my stuff that I demonstrated here at the Vintage Computer Festival is diagnostics specifically for the KIM-1 computer. The KIM-1 computer has two parts on it that are just not available anymore because they're mask ROMs that were made, around 1976. So they're just not out there anymore. One of the problems is, of course, once one of those is dead, especially the -002 part, that part will kill your monitors. You have no way of talking to the computer. So when I had my board, which is here, when I first got it, somebody else had already blown it up for me. So it wasn't working, and I wanted to fix it. I wanted to have it working. I wanted to play with some of the old KIM programs that were available. So I realized that one of the things that a lot of people don't realize, if you have a non-working computer, it's really hard to tell what's broken, even if you have a logic analyzer, without being able to run code on the computer itself. So my intent was to start out and build not only diagnostic code, but a method of introducing the code into the KIM so that the KIM can actually execute that code and do specific things that are easier to take, like a logic probe. As a matter of fact, we did some debug earlier with this fellow's board. With just a logic probe and the diagnostic board, because we can do specific things. Even if you have a computer that's almost working, right, and is executing some code, if it's not executing the code you want it to execute, you're still not going to get very far with diagnosing it, because it could have been anything in the reset sequence that had caused it to fail. So this is my first experience with KiCAD. I'd used a CAD program set up like 35 years ago. So things have changed a little since then. I used a fellow that, we used AutoCAD back then, and there was a fellow in Santa Cruz that had written, if you can imagine this, he had written an auto router and a rubber banding system for overflow wires that was written in AutoCAD's AutoLisp. So this is, and it worked, and we used it for quite a while. We had to do our own part placement, but the rest of the routing was oftentimes auto done, and there was usually one or two overflow wires, and we could push some wires around and correct the routing and get it to work. It was a pretty good enhancement at the time. So anyhow, this is the first time I've played with KiCAD. It's been a learning experience for me. There were a number of features in it that took me a while to understand. One of them I still don't have a grasp of, and that's where my libraries are. I just can't find libraries. I find that I end up, even when they're my libraries, I can't find them. I don't know what I did with it. Their menu system is not intuitive for accessing libraries. The libraries that they have that they recommend you play with on the web are horrible. If you stop by and look at my board, you can see when I started this external board first, and the resistors that are on there. If you look at the layout for the resistors, this is a layout specifically for quarter-watt resistors, and the pins are this far apart, or the holes are that far apart, and I go, who would ever do that with a quarter-watt resistor? Oh well. Anyway, so and you can see that on my board. I got about halfway through the board, and I said, "That's it. I'm not going to have that anymore. That's not the right way to do it." So anyhow, you can see here that I've generated a schematic. You can see for the. Let me kind of get it so I can see it here. This schematic does several things that are necessary for the KIM in order to get this EEPROM that I put over here, so that I can actually run code on the KIM and use that for diagnostic purposes. The most important thing is you want to be able to capture the processor itself from the circuitry that's on the board. The KIM was designed so if you could expand it, you could put external ROMs and it would boot to your external ROMs. So if you look here, you'll see there's a, right here, this is a signal called DECIN or whatever it is. And what that does is that pin, if you ever used a KIM, you'd know you normally have to jumper that pin to ground in order to make your board work at all. Well, if you pull that high, that allows you to have your own external EEPROM on there. And so that's what I use it for. I also decode the address C0 on it as well. So I can, the reason for that is that I wanted to be able to also, once I had the monitor up and running, I could still access code that I put on my EEPROM. So I would access it at what would be K4 on the selects. So that's what a lot of the circuitry is for. There's a couple of latches, oops, excuse me. Let's see if I can. There's a couple of latches on the side that I use to hold the status for the lights. One light is just lights that says that the processor accessed the board. So that's kind of an early diagnostic. And the other one is a little green light that I use for various statuses and stuff. So you can see what's involved in that. When I first laid it out, I went through and arbitrarily put pins, selected pins for the thing, and then back annotated that into the schematic after I realized what my layout was going to look like. And it's pretty straightforward from that standpoint. The thing you gotta understand though is when you're doing the layout of the board, when you tack a point down, all you're doing is tacking one dimension of that wire down, and as you drag the wire, you can still move it around. In other words, it's the last corner that you have that you're actually tacking when you tack it down, and then you move the wire around it shifts. So it's kind of counterintuitive, but after you use it for a while, you realize that's how you really want it to work anyway. You want it to kind of help you get your wires routed through the board. So anyhow, you can see I ended up doing most of. I think these were all cells from the library, but this one and the connectors, I did all that myself because the stuff they had was horrible, and I think that's the last I used of their libraries. Okay, so the first thing I did, like I said, is I needed to create software for the EEPROM, and the EEPROM uses. I start out with a sequence of events. The first one is just to make sure that the processor is alive, that it checks the fundamental things you want to see. That it has reset. You're not generating constant interrupts. The buses are alive. The address bus and the data bus are alive. And so it's a very simple program. All it does is blinks the green light. It executes completely out of the processor. So 6502 usually likes to have RAM, but you can do quite a bit of stuff just on the registers itself. And each of those is selected by this switch. You see there's a switch in here that allows me to select the various banks of the EEPROM. The EEPROM's bigger than the select area that's actually selected on the KIM. The next test I do is a RAM test. I do a stuck at high, stuck at low with the AA55 patterns, and I run that because you have no RAM yet. I run that completely in the 4 registers in the 6502. So you get the accumulator, XY, and you can use the stack pointer as a storage on the side. So by using those registers, it allowed me to generate a RAM test that didn't need RAM to actually execute. And so that allows you to verify that the RAM is good. And then it has a real simple blink routine that you have. I don't know if you stop by my thing, you can actually see it run. If there's a failure, it it starts from the far side and steps across, and it does about a 1 second blink for each RAM. If there's a RAM failure, it does a really short, it just looks like a blit, right? Where the failure is. So you can identify which RAM has failed, or possibly it could be the buffer chip that's tied to the output pin. But it allows you to very quickly identify where your failures are and things like that. It's and again, because it's not using the RAM. Once you've verified you have RAM and the RAM is working, you can use it for other tests. And then I go on, I do a test of the display and the keyboard, and then the actual ROMs themselves. I do a CRC check of each of the ROMs inside of each of the 6530 positions, and that's all the code there is in there. Also, there's RAM inside of each of the 6530s. I test those as well. Once you have that part working, you really don't need much anything else. If you get that part working, all the rest of the things that you would test on the board, you can test from the monitor, which is, real simple programs and, peek and poke and stuff like that, kind of operations to your memory through assembly code. But it's pretty straightforward. So then, as I discovered on my board, the 6530 chip, which for the -002 was defective. And that's a more serious problem because, like I said, that's a mask part that's no longer available. It's people say that's the most common failure, but surprisingly, what I've seen is it's maybe about 1/3 of the failed boards have that problem. Most of the other boards have something else broke. Either the RAM chips failed or something else has failed. So it's, if you have a bad board, it isn't guaranteed that you're going to need to replace that -002 chip. All right, it could be anything on the board. But anyhow, so I built, if you can see here, I don't know if you can see it clearly there, but it's a stack. There are two on the web, Bob Apple, can't think of his, Applegate. Yeah, Bob Applegate has one board that's a replacement, but the boards are, they're like this. And I felt that on the KIM, you wanted something that was just basically, it could be a vertical thing, but it had to fit underneath the 40-pin socket. So that's what I made. I can show you the issues with that. Let me back this schematic out real quick. And go to, I can look at it here. Let me go to this one over here. That's the diagnostic board. Let me look a little further. I just don't remember the names I had for these. I should have looked at them earlier this morning. Yeah, these are the actual. Darn, that's not it. Why am I looking at that? I did several versions of this board because I used OSH Park, and OSH Park gives you a discount if you can get the size to 100 inches for the order. And I actually increased the size of my board so that I could get it to 100 inches. So it was kind of a funny way to actually do it. Let's see if I can find my, here's one. This shows the actual bottom board that's in there. You can see that the routing, this is all 10 mil spacing. And so you can see how I tried to push everything in there that's necessary. There were a couple places where I was able to move stuff around. The 6532 and the 6530 are, the pin outs are almost completely different. So You see there's a lot of crisscrossing, a lot of flipping over to get the pins to actually cross-connect. And so this is the board that you can see here, the number of oddball stuff that there is on that. These holes that are here next to the outside pins are the actual holes that I use to interconnect across from board to board. So those are the what they call interposer connections. And then I tried to put most of them along the line there, along the sides, so that they don't take up any routing space between the pins and things of that sort, because I need those as well. Then you can see here the, let's see if I can find the drawing for it, which I thought was this one. Maybe this one. It looks like that's the same one I just looked at. Ah, yeah, there it is. Okay. Just bad naming on my part. This one here, you can see I looked at various different package options that I could stuff in between the 60 mil spacing. And I looked at pals or gals. They had the rectangular package ones, and those won't fit because they're just too wide, and also they kill off your routing. So I ended up using a standard old style 20-pin DIP PAL in there for doing address decoding and the write enable for the E squared memory. Below is the pads I put in for the E squared memory. Even the E squared memories that I was able to get are a flat pack that lays the leads out this way. And I actually had to fold the leads under, flatten them down, and planarize them on a piece of sandpaper in order to get it so I could squeeze them into a narrower pad arrangement. So I created all these pads myself in order to actually do that. And that worked out pretty well. The first time I did it, the pads my first version were a little narrow. And at that time, I could only hand solder because I don't have an oven to heat them in. So I actually, hand soldering was difficult if you can't heat the pad and the lead at the same time. So I made the pads a little wider. There was enough room there. You can see there's enough room for the routing and stuff. So I was able to get all the routing and things that I needed there. There were a couple cases where I had to, because, if you look at it, anytime you punch a hole through, you lose some routability space. This is one of the things people don't really grasp sometimes when they look at how many layers that you can put on some project. They think, well, I put 10 layers, maybe I'll put 12 layers in there. Actually, you'll find that you may not be able to route a 12-layer board because you've already used up too much space for the feed-throughs. The feed-throughs take a lot more space than the traces do. So you have to be conscious of that as you're working along. You want to try to minimize the number of holes that you put through the board or from layer to layer, because you chew up your routability more than anything else. You might want to look at maybe moving stuff around more and optimizing the positions of it, or usage of your I/O pins and things of that sort. So that's about it. The E squared, I actually program it physically on the board, on the KIM board itself, with the code in the diagnostic memory. I don't have an adapter for that little tiny package, and of course after I folded the pins under, it's not even the same anyway. So, yeah. Any questions on that? What? The other layer? Yeah, there's two layers. This is both layers. If you look at it, you see the red wires are one layer and the green wires are another layer. Excuse me? Yeah, you can see that there's a red and a green. Yeah, it's a little hard to see from a distance. The red wires are on the top surface where you put the solder mask and things, and the green wires are on the bottom surface. Those are all optional selectable things on the KiCAD package. You can change the colors if you don't like green and red. That's kind of just various optional things that you can set up. The main thing about when you actually start KiCAD is you want to first check to see who the vendor is that's going to do your boards, because each vendor has different rules about minimal hole size and spacing of the leads. So I got pretty close to the limit for OSH Park here at 10 mil spacing. There's a setup that you do inside the KiCAD to actually put those values in. And it will automatically keep you from accidentally putting a trace too close. But if you take the default stuff, you'll find that it will be wrong. And you may actually end up generating boards that the board house will send back to you and say, no, we won't build this board because you've tried to put these traces too close together, or you put a hole that we can't create, or something of that sort. So it's always best to check with the board vendor first, exactly what they can do. OSH Park, I think, has a minimum spacing setting of 7 mils. So if you're doing 10 mils, which is more convenient, it's, from a placement standpoint, the 10 mils is adequate. But you could push it a little more to 7 mil, which about every 3 or 4 lines will give you an extra line that you could stuff in there. So it's, one of the things you have to watch out for, but definitely you want to understand how that mechanism works, because it will work in your favor. It's also handy if you particularly want to guarantee that you have some places where you want more spacing between things and less spacing. You can alter that as you go. It doesn't go back and worry about stuff you've already laid out. So you can use that as kind of like an auto mechanism to control, how your spacing is in different parts of the board. Like you say, in one place I want it to be 10 mils, another place I want at least 20 mils space, or I want bigger traces, I want smaller traces, whatever, right? So you can run around, and that's okay. AutoCAD, KiCAD also has a feature in it that will allow you to fill empty space. So say you wanted to make, you're doing a 2-layer board. You notice my 2-layer boards are all traces. I don't have any power planes or any of that thing on them. A lot of people want to put power and ground on the bottom and the top. And once you've got all your traces routed, you just tell it that you want this power lead to be a fill on the top layer or fill on the bottom layer, and it will take all the empty space and try to connect it up. And then it will, in the wire routing, it will leave the, if you can't get it connected, it will leave rubber band or rat's nest connections there, so you can hook up your power leads. So that's pretty much it. Any other questions that anybody has that might be? Yeah. Yes. Yeah. Most of them are doing plated through holes now. So, they realize that 2 layers without plated through holes is kind of useless. And you can do it, but it's really difficult. But yes, these are plated through holes. OSH Park, they're not the cheapest out there, and they will do this purple colored board. But I found them easy to work with. I made some mistakes in ordering, and I wrote emails back, and they fixed it right away for me. It was like I accidentally ordered two of one of these boards instead of one of the top and one of the bottom board, stuff like that. And they immediately got back to me and tended to it. I was very impressed with their quickness. Yeah. No. No, I'm not a web person. I tend to not, other than in emails and things like that. I guess that's about it. But yeah, I could mention a little bit about the code. As he knows, I'm a fourth programmer. I only use C and other things at work. There, as far as I'm at home, I find it to be those other languages to be terribly clumsy. And so even the assembler, I don't use other people's assemblers. I always write my own assembler. I find that the assemblers that every people have just don't have macro capability that I like to have. With using the fourth as a base behind the assembler, I can write infinite types of macros. The ones I use for this were all pretty trivial. If you look at my code, if you stop by and look at the code that I have in the book, you'll see that I don't have any useless labels in there. There's no L1, L2, L3 kind of labels out there because I do all the code with structures. I have begin until structures, if then else kind of structures, do while repeats, whatever. So the code is all built that way. I very rarely actually put a branch instruction as a branch instruction in my code. I do. There's purposes for it, but most cases I use one of these structures to create the branches for me. It has an auto feature in it where if the branch is more than 128 plus or minus, or I guess 127 one way, 128 the other way, if it's more than that much distance, it will instead of putting the branch to that address, it will put a branch over the next instruction, which would be a jump instruction. So it automatically takes care of those kind of things for you as part of the macro function. And those are things you'd like the assembler to do for you, but it needs a little intelligence to do that. So, and then also, I started a long time ago writing single pass assemblers. I think double pass assemblers are a hazard waiting to break. And so in a single pass assembler, you often find, first off, you think, well, how do you do a single pass assembler? You're going to do forward branches someplace, right? Well, the kind of forward branches that I do are mainly things like the vector, the reset vectors, and things like that. So I have a word that I call segments. I define a segment, so like I might define a segment called main code, right? And I might define a segment called NMI reset or interrupt vector. And then I would take those, and if I use that name, it's assembling code in that particular area, and then I can switch back and forth, names back and forth. It keeps track of where it left off from the last time I was using that area name. So it allows you to do all your forward references where they're explicit addresses. In some cases, you need to do forward we just need a label. So I have a function that just does a forward label. They just have to be predefined as a label. You say, I'm doing a forward label. I just have an F label is what it is. And it says it's a forward label. And then it knows later on when you actually define the label that it needs to be patched. So it creates what's called a linked list where it keeps track of what all of the forwards were. And each location where it actually is referenced, it keeps track of what kind of reference it was. The only thing you can't do easily with forward references, you can't offset them easily. So if there's a calculation involved in it, I don't have anything for that, but that could be done. So if it's a label that you're going to add 5 to, for instance, for the actual vector that's going to be created. But in those cases, it's usually better to just have an explicit label for each thing that you want anyway. There's rare cases where you might not like that. But anyhow, that's it. You can stop by the thing and see that, see how that looks. I have the source code for my assembler here if you want to look at that. I have also the various different diagnostic tests that I have. You can see how they're arranged. That's it. Any more questions? Interesting? No? Okay, thank you.